Hello everyone. Today, as stated, we will, in the title, we are gonna discuss interface condition, magnetic interface conditions, and we're gonna introduce the concept of inductance. Right? How do I delete this? Cut. Okay, I'll ignore this. All right. So we're gonna introduce the concept of inductance today, and you're familiar with inductance from circuits, of course. I mean, but we're gonna introduce it from the field perspective. The lumped perspective, of course, is the circuit perspective. In the same way, we introduced capacitance from the field perspective. Okay, but let's start with magnetic interface conditions, which is very similar to electrical interface conditions, right? But right, remember in electrical interface conditions that the tangential components were continuous, while the tangential field intensity vector E was continuous, while the normal flux density component was also continuous, except if there was a charge density at the interface, right? What does, in contrast to electrostatics, how does the interface condition look for magnetostatics? Well, the first thing is to state the problem, right? So we have two materials. Always we have material 1 and then we have material 2. Material 1 has mu1 permeability, material 2 has mu2 permeability. And then to get the result in general, we assume that there is some kind of surface charge density, meaning the charge density flowing into the interface. This X means that the current is flowing into the interface. It's like a sheet current. Okay, so it's current that's measured in amp per meter. Every unit length has a certain amount of current flowing into it, right? And then the question is, if we have of course, we always assume that there's a unit vector, reference unit vector that's normal to the interface, pointing into material 1. That's a convention, right? And then if we have like the field just at the interface, and then the field just at the interface in material 2, right? H2, right? When we said the trick is to always decompose those fields into a tangential component. So I have H2T, H1T, not H1T, sorry, H2N, H2N, and then decompose this into, again, a normal and tangential component. So this is H1N and H1T. Okay, so let's start with the tangential component. Here we apply Ampere's law. So we select a contour like this, right? And then I need to let me select the direction of the contour to be clockwise like this, such that I'm applying the right hand rule. I want to select the direction of my contour such that if I apply the right hand rule, my thumb points towards the direction of the current that's flowing on the sheet, right, on the interface. The current is assumed to be flowing inwards. So I use this clockwise direction to get the right hand rule correctly, right? And then I apply Ampere's law, of course. That's the trick, is applying Ampere's law, which is I enclosed. Okay, so applying Ampere's law, I get H1T. The direction is the same direction as H1T, and then when I go to this region, the direction becomes opposite H2T. So this is H1T delta L, assuming the length of this contour is delta L. The width now, delta W, here is assumed to approach 0, of course. so that we ignore the normal component. Right? So applying Ampere's law, H1T delta L times minus H2T delta L equals Js. What's the total in-cross current? It's the surface current density times delta L. So ampere per meter times meter gives me amperes. Right? Clearly delta L goes away here, and I end up with this condition. H1T minus H2T equals Js, ampere per meter. Okay, and that's the condition for the tangential components. The tangential component of the magnetic field intensity are continuous unless there's surface charge density. Right, and the contrasting B field is going to be just H is just B over mu, right? Mu1 minus B2T over mu2 equals Js, right? Now, here we have to remember the right-hand rule. So if I, in my selection of H1 and H2, my selection of direction of H1 and H2 depends on my selection of the ampere surface, the ampere contour, right? And when selecting the ampere contour, I have to always be mindful of the right-hand rule. So there's a question of what do you need, but what do you select for JS when you plug in JS? What do you select? Which direction do you select as the positive direction for JS? So that can be tricky, and you have to always be aware that the right-hand rule, according to Ampere's law, needs to apply. If you don't want to think about that, you can just use the vector version of of those two expressions. And the vector version is simply, I mean, the only thing you have to remember is that n hat points towards material 1, right? If n hat, the normal vector on the interface, points towards n1 inside into n1, then all you have to remember is this formula, n hat cross h1 minus h2 equals js, and this automatically takes care of the right-hand rule. Okay, because if I point my thumb towards n hat, right, and then point my fingers toward so let's say I have h1 minus h2, so I select, right, right, so yeah, so if I apply the right hand rule to n hat, to the cross product between n hat and h1 minus h2, I automatically get the correct direction for j, so I don't have to think about it much. Right? So this is the way I would remember this first interface condition, right? And then I can of course write it as n hat cross b over mu1 minus b2 over mu2 equals js. Right? So here imagine this is interface. This is h1. This is h2. I take the difference between h1 and h2, and then n is pointing in this direction. Right? So what is n? So let's say this is the difference. This is the delta h. What is the cross product? Applying the right-hand rule, the cross product, if delta h is positive, the cross product will automatically tells me that j should be pointing inwards. The cross product automatically gives me the right direction. Okay, it has the right-hand rule embedded in it. Okay. Now we go to the normal components, and the normal components, for the normal components, we have to do the same thing as we did for electrostatics. This is minus n hat. We apply the Gauss's law for magnetostatics, right? So we have this cylinder, the width goes to 0, and anyway, it doesn't matter because the normal component is cancels out, it's parallel. But what we want to cancel out also is the tangential component, so we need to take delta W to 0. Okay, and then I have, let's say B1, I have B2, right? And then I only care about the normal components, B1n. Applying Gauss's law for magnetostatics, I end up, let's assume that this is the surface area, I end up with B1n S, because B1 is pointing outwards while B2 is pointing inwards, right? Minus B2n S equals 0. So I end up with this condition, B1n equals B2n. So this is the interface condition for the normal components of the vectors, right? And notice the flux density, the magnetic flux density is continuous, while the field intensity is not. So here it's going to be mu1 h1n equals mu2 h2n. Okay, so it's very easy and quite analogous to the electrostatic case. Now, magnetic fields exhibit refraction in the same way that the electrostatic field exhibits refraction, and it has to, right? Because ultimately we said, remember, we said that in the beginning of the course that light is a form of electromagnetic wave. So, and we know light refracts, right? So so we should expect both the electric and the magnetic fields to refract. I wouldn't expect only one of the fields to refract. So so in this diagram, if I consider this to be theta 2, and consider this is the angle of the incoming field, H field in material 2, and then the outgoing field, I guess I want to have theta 2 with theta 1 with respect to the normal. So this is theta 1, right? So according to this diagram, theta 2, what's the tangent of theta 2? The tangent of theta 2 is H2, the tangential component over the normal component. Tangent of theta 1 is going to be also the tangential component over the normal component. So I end up with those two expressions for tangent theta 1 equals h1t over h1n. Tangent theta 2 equals h2t over h2n. And then what happens if I divide tangent theta 1 divided by tangent theta 2? I get h1t over h1n divided by inverse of tan theta 2. I end up with h2n over h2t. Now we said from the interface conditions that h1 should be equal to h2 if there is no current in the interface. And let's assume there is no current. Most cases there won't be a current in the interface, just like electrostatics. Then the normal components will be equal. What did I say? No, not the normal components. The tangential components will be equal. Okay, so I end up with h2n over h1n. What's h2n? It's b2n over mu2, and this is b1n over mu1. Why did I change it to b? Because now I know that for the normal components, the b fields are equal. So this cancels with this, and I end up with tangent theta 1 over tangent theta 2 equaling mu1 over mu2. This is Snell's law for magnetostatics. So refraction as a phenomena is not dependent on the fields at all. It's only dependent on the material. Okay, on the proportion of mu1 with respect to mu2. Okay, so those are the interface conditions. Again, very simple, very similar to electrostatics. Okay, now I want to talk about inductance. What is inductance? Very similar to capacitance. Capacitance turned out to be a lumped parameter. We looked at a system, a configuration of objects, and we extracted like just a single number that represents somehow the capacity of that object. Meaning if there is a certain voltage, how much capacity that object has to hold charge, right? In a similar way, inductance is a lumped parameter. We look at a system, in this case, because in electrostatics we had charges, the sources were charges, and we had the fields. The system looked at capacity between voltage and charge. How much voltage gives you how much charge in a certain configuration. Inductance, because magnetostatic fields normally arise from currents. I mean, this is the source of the field. The capacity here is between current and flux. So the question is, for a certain configuration of wires, if we have a certain amount of wires, we could have loops of wire and whatnot. For a certain current into that configuration, how much flux do we get? That ratio between flux and current lumped into a single parameter is inductance. Let's discuss this a bit, okay? So, B equals mu h. Okay, let's examine the units a bit, the units of mu. So we said mu has the units of the flux density. The flux density is Tesla or Weber per meter squared, divided by the units of H. The units of H are ampere per meter. Let me write this. I end up with Weber over meter squared times meter over amp. Cancel with meter. I end up with Weber over amp, right, times 1 over meter. Right? So this term seems to be some sort of capacity. For electrostatics, it was Coulomb per volt, and we called that the capacitance. This is another kind of capacity. Remember when we said the Weber can be considered the charge of the hypothetical magnetic, the charge of the the unit of charge for the hypothetical magnetic charge source. So yeah, WB is just magnetic charge in the same way that Coulomb is electrical charge. Of course, this is mathematical. There is no magnetic charges, as we keep saying, right? But this could be considered as some kind of capacity where a certain amps is going to give you a certain amount of magnetic charge, right? But we have that difficulty in that magnetic charge does not exist. How do we understand? How can we better understand this, right? In electrostatics, it was easy. We just had Coulomb over volt, right? And we could interpret this correctly. We didn't need to do Coulomb over meter squared times divided by volt over meter squared. That didn't make sense. Volt over meter squared did not make sense, right? In this case, Weber over amp doesn't make much physical sense to us. Yeah, we can imagine it as in space there is some polarization that exists everywhere, that is a bunch of magnetic charges that are bound charges and whatnot, but that's kind of like we can think of it that way, by the way. We can, right? But we don't need to. We can better understand this capacity by doing this trick. So I'm going to take this capacity, this amount of Weber that we get from a certain unit of amps, right? Amount of magnetic charge that we get from a certain unit of current, electrical current. And the trick is that we divide both numerator and denominator by m squared. Nothing changes if I do that. I divided the numerator and the denominator by the same thing, right? But what is this? This is for me more physically meaningful. Weber over meter squared is magnetic flux density, right? So this is flux density. And amp over meter squared is current density. So this capacity is what's called inductance. It's like a measure of this is of course inductance density over 1/meter. So this is no, this is inductor. Yeah. So this is just a measure. Let's just call it inductance. This is a measure of how much flux we get versus the current that's flowing in the space over a very small volume in space per meter. Right. This unit now is called Henry. This sort of capacity. Okay. Now the usefulness of this capacity, just as in the case of capacitance, we could study capacitance for small volumes of space, right? That's fine. So farad per meter, for example, here in this case Henry per meter. So here we're studying capacitance per unit of space, right? So we have space and then we have capacitance per unit of space. It could be very small, it could vary, we can integrate over it and whatnot, right? And then we have capacitance in terms of flux versus current per unit of space, right? But so we could study it from that perspective, but the usefulness of inductance as a concept is that it gives us a lumped parameter. So the way we study inductance is we look at a whole system, that has a bunch of wires in it. Could have one wire, two wires, three wires, doesn't matter. And from just the configuration, we want to get one number that links the currents in this configuration versus the flux that appears in the system. So the total flux that appears in the system versus the currents in the system. Right? When we link those two things using lumped constant parameters that do not depend on the currents and the fluxes, they just depend on the configuration. That's where the usefulness of the concept arises. It allows us to reduce a complex configuration to its essence, reduce it to one number that expresses how the current leads to the amount of flux, so on and so forth. Right? So we want to get a lumped value of inductance that is essentially gives us a handle on flux over current, and flux equals inductance times current. Right? So you remember capacitance equals Q over V, right? Or CV equals Q. So in this case, the total flux is analogous to the total charge, and the current is analogous to the voltage, and it's exactly analogous, by the way. Voltage is in volts, charge is in coulomb, right? And this is in farad. L is in amp. What's flux? What's the unit of flux? Flux density is Weber per meter squared. That's the unit of B. Flux is just the integration of B over a surface. So the Weber per meter squared times a meter squared. So the unit of total of flux is Weber. And remember, we said Weber is the unit of magnetic charge. Coulomb is the unit of electrical charge. So the analogy is complete. So I have here volt, Coulomb, I tie volt to Coulomb. Here I tie ampere to Weber. Okay, let's go a bit in detail. How do I define inductance for certain scenarios, right? And in a certain way, inductance also differs from capacitance in one big way. In a system, if I have a system, typically I'm concerned with capacitance between two objects, two conducting objects, right? For inductance, it gets a little bit dicier because I could have a bunch of wires that are more than a single wire, right? So I could have wires, I could have loops, right? So I could have inductance in a single loop. I could have inductance between like this wire and this wire, inductance between this wire and this wire. So inductance could have could vary depending on the two objects that I'm studying in the configuration. Okay, while for capacitance we can just study it, zoom in into two objects and study capacitance for those two objects, and then any other object will not affect the capacitance, will not affect that single object. But for inductance it's a little bit trickier. I'll show you why. Okay, so let's look at the classic example. Okay, so I have two loops. I have loop 1, I have I1, right, and I have surface area 1, and then I have a second loop. This is a configuration, my configuration, and I will get the lump parameter in this case, right? So this I1 causes flux, and this is S1 and this is S2. This is loop 1 and this is loop 2. So this I1 causes flux to appear within S1, inside this first loop. So I call this flux 1, 1. 1 here means this is the flux due to loop 1. The first number means which is the flux, where is the source of the flux. This is the flux due to loop 1. The second number is where is the flux, where does the flux exist. The flux exists within loop 1, right? But then this flux goes out and affects loop 2, right? It passes through loop 2, right? So there's the flux originating from loop 1 within loop 2. So there is that flux, right? And we said we defined inductance as the lump parameter that gives me a single number that ties current to flux. In this case, there are two fluxes, two different fluxes. That's the main difference between electrostatics and capacitance and inductance. Because in capacitance, when we link voltage to charge, the charge between the two objects is the same, does not change, right? Has to be the same. While the flux between those two loops could be different. It depends on how far the loop is, right? How differently shaped the second loop is, how different the area is. That's why we get multiple values for inductance. So there is one inductance that gives us the lump parameter between I1 and the flux within loop 1, right, which is generated by I1, and then the other parameter that links the flux in loop 2 due to loop 1, I1, and we call this one 1, 1 and this one 1, 2. We match the flux, right? So there are two inductance parameters in this case, right? And those two parameters depend only on the geometry, only on geometric configuration. Okay, this is called the self-inductance, because I1 passes through the loop 1, it generates a flux in loop 1. The relationship between the flux in loop 1 versus the current that's generating that flux is called it's relationship between I and its own flux. So that's why it's called the self-inductance. L12 is called the mutual inductance, right? Because there could be a different current passing through C2. So this is the flux going through the C2 is not due to a flux that's generating. It's not a flux that's being generated by the loop itself. It's coming from an outside loop. So that's why we call this mutual inductance. We could write it another way. L11 equals the flux over I1. And the units here are Weber per amp, which is Henry, right? And then the mutual inductance is flux 1, 2 over I1, right? Which is Weber per amp, also Henry. Okay, So the phenomenon of inductance as a lump parameter, that's an interesting thing about it. You have in a certain configuration, you might have different inductance values. You have self-inductances for every object. How does this object link between the current and the flux generated by itself? And then how does that flux travel and affect other objects in the configuration and the mutual inductance that arises? Okay. What happens to the case where we have like a bunch of winding that's loop that's a bunch of windings, right? We have N1 windings, right? So let's assume we don't have just a single loop wire, we have a bunch of windings. Okay, that will change the definition of the inductor, right? That will, for a very subtle reason, I'll explain it to you now. So we said the point of the value of inductance is to link, so this is I1, to link in a lump, we're using a lump parameter, the flux, this is flux 1, flux in loop 1 due to the current in loop 1. This is flux in loop 2 due to the current in loop 2. Sorry, flux in loop 2 due to the current in loop 1. Right? And we said we want a parameter that links, I1 to phi11 and parameter that links I2 to phi12. That's what inductance is. It's a lumped parameter. Right? So we would be tempted to just do the same thing in the case where we have multiple loops, right? But we could just say what L11 or L12. Okay, that's fine. We could say that, but that's not how things were developed traditionally. What happens here is that by definition, to make the concept of inductance useful, we define this lump parameter, we factor into the lump parameter somehow. And I'll show you how in this way. We define the lump parameter to be L11, the inductance, divided by N1. And we define this to be L12 divided by N2. Why do we do this, by the way? There's a deep reason why we do this. I mean, this is just a constant, right? I could have put anything there. Why did I have to factor in N1 and N2? The reason I had to do that is multiple reasons, but the one big reason is for energy considerations. From circuits, if you calculate the energy, you end up with the energy for an inductor being half L I squared. This only occurs if I define L this way, for the case where I have multiple loops. If I don't define L this way, for the case when I have multiple loops, I will have N in the energy expression. We don't want that. So people agree to define the lump constant this way when we have multiple loops. The other reason, which we will talk about next next lecture, in our last lecture, is due to Faraday's law. So I'm gonna briefly just mention it. If I differentiate with respect to time, right hand side or left hand side, I end up with d phi by dt equals L11 over n di1 by dt, right? If I didn't have the N1 here, we know from Faraday's law that the voltage is proportional to n d phi by dt. So I end up here with V equals NL di by dt. Right? This is an ugly formula, right? I have this extra parameter I have to worry about that has nothing to do with the it has to do with the configuration, but I don't need it. It's an extra parameter, right? So if I assume that the lumping constant, the inductance is the lumping constant between I and phi for the case of multiple windings is L over N instead, I can take this N to the other side and I end up with the simple lumped circuits formula. V equals L11 di1. by dt. So that's the main reason we kind of like do this weird thing where, hey, we said, yeah, inductance is the lumping between I and phi by a single parameter, but when we deal with a situation where we have windings, we define that relationship this way. We factor in the number of windings, right? So, and the reason is to get those nice formulas for the energy and the relationship in circuits between the current and the voltage. That's the only reason. It's a matter of choice. Okay, so that lets us arrive at the final definition of the inductance. Final definition of the self-inductance is N1 phi11 over I1. N1 phi11 is called the flux linkage. So it's the flux in the loop times the number of turns in the loop. So this is called the flux linkage. Flux linkage, which I hope I gave you like somewhat of an idea why we do this, right? For aesthetic reasons, to get the nice circuits formula, right? And then L12 equals N2. I take N2 to this side, phi12 over I1 equals lambda 12, the flux linkage between loop 1 and 2. Okay. So this is the final definition of the self-inductance and the mutual inductance. Okay. Right. What about the case where, so I have this winding and then this winding, and I said I had I1, right? What if I had I2? Right? Well, if I had I2, there's also going to be self-inductance for loop 2 and then a mutual inductance between loop 2 and loop 1. So all we have to do is take those formulas and flip the indices. So it's going to be self-inductance for loop 2, and this I'm going to have N2. I'm just flipping the indices, phi22 over I2, and then flip the indices. Mutual inductance between loop 1 and 2 is going to be N1, right? Instead of 1, 2, N1, and then phi 2, 1, meaning the flux in winding 1 coming from loop 2 over I2. Right? So really I have, in this configuration, I have 4 sets of parameters to completely describe inductance. I have the self-inductance of loop 1, the self-inductance of loop 2, and I have the mutual inductances 1, 2, and L2, 1. You will find out, and we can show that from energy considerations, from symmetry, that the mutual inductances always are equal. So L12 equals always L21. This is a fact. You can always utilize that. Right? The more interesting thing is if you have multiple loops in your configuration, and this is something that doesn't happen in magnetostatics. In magnetostatics, I know I drew the loops terribly, right? In magnetostatics, in electrostatics, sorry, this is something that doesn't happen in electrostatics, because always in electrostatics the charge is equal when you have, you know, multiple. You might have a configuration where you have, you know, a bunch of capacitors in series or whatever. So it doesn't give you as rich possibilities for the configuration as magnetostatics. Ultimately it's due to the existence of the electrical current, while in electrostatics there is no magnetic current. If there was a magnetic current, a bunch of magnetic charges that are moving, then yes, the concept of capacitance will be as rich as the concept of inductance, and we will have multiple self and mutual capacitance. But I don't want to go to that a lot, right? But let's say we have 4 windings in our configuration. In this case, we will have 16 parameters for inductance. We will have all the self-inductances, and then we will have all the mutual inductances. The mutual inductance between winding 1 and 2, between winding 2 and 3, between winding, 1 and 3, between winding 1 and 4, so on and so forth. So we can fill up a matrix of self and mutual inductances. Okay. All right, so that's an introduction for the concept of inductance from the field perspective. And this is the hope you can like solve some exam. I mean, we don't have time anymore, unfortunately, in the course to solve examples and whatnot. I hope you can go through a number of examples in the book, but I just wanted to cover it conceptually. Okay. The other thing I wanted to cover is the energy in the magnetostatic fields. Okay, and I won't derive this. I'm going to give you the result. The reason I don't want to derive this, again, other than we pretty much ran out of time. I mean, hopefully, I think we got a good overview of everything. Some things we went into more detail in, right? But I think given the circumstances, we cover a good portion of the material. What I want to do, however, I want to utilize the last lecture or so to give you like a taste of Maxwell's equation, because that will be like the crowning result from this course, right? And hopefully you're interested enough in this material to kind of like study a lot of stuff on your own, right? Okay, so yeah, so that's why I won't derive the energy in magnetostatic field. I'm just going to present you with energy from the field perspective, and I'm just going to tell you that all the derivation that we did for the electrostatic field, it's essentially the same thing, that we just have to repeat, right? And we get the same concept. We get even the same form for the energy, right? So the energy density in terms of joules per meter cubed can be expressed in two ways. Can be expressed with respect to the vector potential, magnetic vector potential, and the current density. So this is joules per meter cubed. And remember, in electrostatics, from the vector perspective, the energy was proportional to the charge density versus the voltage, right? Something like this, right? So it's essentially the same thing here. Instead of scalar potential, we have vector potential. Instead of charge density, we have current density. And then from the field perspective, the energy density is just B dot H over 2. For the electric case, the energy density was just half D dot E. So notice it turns out to be the same thing. It turns out to be the flux density vector dotted with the field intensity vector. Right? So you should know this result, and if you're curious, you can derive it. But suffice to say, the derivation is analogous to what we already did for electrostatics. Okay. One final thing I want to say. Oh, what is the total energy? The total energy in this case is going to be just the volume integral of B dot H dV over all of space. Okay. One thing I want to say is that this opens up an easier way to calculate inductance. Let's say self-inductance for a configuration. Let's say I have a configuration, a wire, right? And I want to calculate the self-inductance. We know from circuits that the energy is half L I squared, right? So that tells me that L equals 2 times the energy stored in the inductor over I squared, right? But then I know that I can calculate the energy from the perspective of the field. I know that the field, the magnetic field, carries energy. So the energy in the inductor really is the energy in the magnetic field. And we know how to calculate that energy, right? So it's B dot H. So I can easily say that L equals W is half this integral. 2 cancels the half, so I end up with 1 over I squared integration over the whole volume of B dot H dV. And in some problems, this is easier to calculate. So instead of finding the flux and then linking the flux to the current, in some problems it's easier to just, we know the B field and the H field, it's easier to just find the total energy using the B and H field and then divide it by I squared, and we get the inductance. So this is an alternate way of calculating inductance. Okay, so I want to go through one example and then I want to be done with this. Oh, by the way, something else I want to mention. Right, so what did we said inductance is defined ultimately as linkage over current, right? So inductance, self-inductance, let's say, is linkage over current, and linkage is really what is N phi, right? N times the flux. So right. So what did I want to say? What I wanted to say. Oh, okay. Right. So what's the units of linkage? The units of linkage are turn. I mean, turn is not a unit. Turn is just a number. It's dimensionless. But let's call it turn per Weber. Right. And then we said the lumped relationship between I and the flux is just L over N, right? So I take N and that way. So this is L over N is the lumped relationship. So this is going to be Weber. This is going to be amp. And then we said this is Henry, right? Because Henry is Weber over amp, right? So amp times Henry gives me Weber. Okay, so in a way, I mean, this is kind of pedantic, but we can think of it that way. L really does not have units as inductance. The concept of inductance in circuits does not have units of Henry really. What it has units of Henry turn, right? It has a unit, so L as a parameter, the L that you see in circuit theory and the L that you think of as inductance is not really Henry. It's kind of Henry per turn. That's what it really is what it boils down to. It's not Henry, it's Henry per turn. But because turn is dimensionless, turn is just a number, we ignore it and we just say Henry, right? But a more proper way to think of L as Henry per turn. Okay, I just wanted to bring up this point. Okay, now I want to do an example just to give you a taste. Okay, so I want to revisit the torus. So remember the torus? It's something like a donut-shaped material, with a certain mu, and then I have a wire that's just twisting. And we calculated the magnetic field due to this, right? So this has at any distance r from the center, we know of course we can look at it from the side. right? And then from the center, this has distance d, and then the inner radius is b, and then the width is c. Okay, we calculated already the flux density for this torus using Ampere's law, and it turned out to be mu Ni over 2 pi r, Weber per meter squared, or Tesla. Weber per meter squared and Tesla are the same units. Okay, so we need to calculate the inductance of this torus, the self-inductance. We need two things, right? We need the flux and the current, and we have N, right? That's all we need to calculate the inductance. What's the flux? The flux is going to be the surface integral over a cross-sectional surface. So that's where the flux is crossing. It's cross-sectional surface of the torus. So that B dot ds, right? And we need to do this integral, by the way, because B is not uniform. B is a function of R. So I have to take right at each R. I have different. Oh, one assumption here I'm making is that this is sort of a rectangular torus, meaning the cross-sectional area is rectangular. It's not circular. It could have been something like this, but that would have complicated stuff. I would have to find the area of the circle. So one easier way to solve this, or this distance, one easier way to solve this is to assume that the cross-sectional area is rectangular. So how do I solve this? I mean, if the flux B coming out, passing the surface is uniform, it's easy. I mean, just B times the area of the rectangle, the cross-sectional area, right? But this is not, the B is not uniform. So what I need to do is I need to make this cross-sectional area, right? So this is the axis, this is distance B, this is distance D, and I need to divide it into intervals. So I take a small portion of the area, infinitesimal area. So I need to divide it into strip. Each strip has an area of dr times c, this is c, cdr. And within each strip, I can assume B to be almost constant, can assume B to be constant, and then I sum it up. This is just how I do the integration. So instead of ds, this surface area can be turned into a single integral where I sum up across those strips. I sum up all those strips, and I get the total flux. Right? So this is going to be B. Instead of ds, I have c dr. That's a small ds, and then to sum over the whole area, r has to go from B to D. That's where r is going. R is going from B to D. So I turn this double integral into a single integral of strips. Right? And then I know what B is. B is mu Ni over 2 pi integral from B to D. And what's left? What's left is, oh, there's C. What's left is dr over r. And that's just mu Nic over 2 pi. What's the integral of 1 over r? Is the logarithm. So this is len d minus len b, which is, we said we know the property of that, len a minus len b equals len a over b. That's the basic property of the natural logarithm. So I end up with len d over b. So this is the flux. Okay. I have the flux, I have I have N. What is the flux linkage? This flux going through the torus is passing through all the windings, right? So there are really N windings that the flux is passing through. So the flux linkage is just N phi, right? So the flux linkage, oh, this is by the way Weber. So flux linkage is going to be mu N squared I C over 2 pi ln D over B. This is Weber dot turn. I'm going to add the turn even though it's unitless, right? It's dimensionless. And L now is the linkage divided by I, right? So this is going to be, so the I goes away. So it's the same thing here as this expression without the I, because the I is divided out. So I end up with the inductance being mu N squared C over 2 pi ln dB. Notice that all the parameters in this expression for L only depend on the geometry of the torus and the configuration of the torus. They depend, and the material. They depend on mu, depend on N, depend on C, pi, dB, right? But they do not depend on I or depend on flux or anything else. Everything distills down to just the geometry of the material. Okay, so with this example, perhaps try to, we'll finish, we'll close on inductance. We cannot do more due to running out of time, but hopefully at least I'm glad we were able to, introduce it a little bit. Okay, and you can go through a bunch of examples about it from the text. If I give a question about it in the exam, it will be similar to one of those simple examples in the text. Okay, I won't give you something fancy in regards to inductance. All right. All right. So this is it, and next lecture will be the last lecture, and it's gonna be. I'm excited about that lecture. We're gonna finally introduce the complete set of Maxwell's equation and give you an idea about how Maxwell arrived at those equations. All right. Looking forward to that, and thank you. Talk to you next time.